This lesson deals with the series equivalence of impedances. You can find these notes in the ECE202 ebook in Chapter 8, starting on page 17. Let me start by stating the theorem. If K impedances are connected in series, the equivalent impedance is the sum of the K impedances. You can do this graphically. Here's an impedance Z1, Z2 through Z sub K. To be in series means you share the same current. You can replace these by a single impedance whose value is Z equivalent, which is the sum of the K impedances. Now, why would this be true? Assume that this rest of the circuit produces a voltage V sub S. Current would have to come out of its terminals because we're absorbing power. So we'd have a drop across Z1, Z2, Z3 through Z sub K. The rise in voltage equals the drops around the loop in the frequency domain. So the voltage V sub S is equal to V1 plus V2 through V sub K, all of which are phasors. But by Ohm's law, voltage here is the current times the impedance. So that would be, say, I sub S times Z1, but also I sub S goes into Z2 through Z sub K because they're in series. So each one of these has an I sub S multiplier. We could pull it out in front, and we're left with I sub S times Z1 through Z sub K added together, and of course that would be the summation of those impedances, and we could just call that Z equivalent. So if we were to replace these K elements by a single element, for the same voltage we'll get the same current. This of course is very similar to what we did in the time domain in ECE201. I'll talk some more about this in a later proof. Z equivalent will be a complex number. We can express it in rectangular form as having a real part and an imaginary part. Let's call the real part R. In general, we'll call it just resistance, and it'll have units of ohms. Let's call the imaginary part X, and we'll give it the name reactance, but it too will have units of ohms. The terms impedance, admittance, resistance, and reactance were coined by Oliver Heaviside in the late 1800s. If you want to read more about him and other historical figures in electrical engineering, just go to the ECE202 homepage and you'll find a button for historical figures. When we're dealing with passive circuits, the resistance term in our equivalence will just be strictly positive because all we got are resistors. The reactance term, though, could be positive or negative because we have inductance and capacitance, and they have impedances that are positive and negative. If the net sum of our equivalence is positive, we could say it's an inductive reactance and that we could model it with a single inductance. If it turns out to be negative, we could refer to it as capacitive reactance because we could also, again, represent it by a single capacitor. These are some of the properties of series equivalence of impedances.